So in this video we'll look at Hess's law. Hess's law is section 5.6 from Brown-Lemay-Burston's 13th edition, and we're on page approximately 226 in the 13th edition text. Hess's law allows us to calculate the enthalpy for a reaction from tabulated values of enthalpy values from other reactions. Hess's law states that the enthalpy of an overall reaction is equal to the sum of the enthalpies of the individual steps. So we can find the delta H of some reaction that we don't know the H for by knowing some other reactions that we can manipulate, either turn around or multiply by something or divide by something. So let's take a look at sample exercise 5.9. And in sample exercise 5.9, it says calculate the delta H for the combustion of carbon to create carbon monoxide. So this is actually really difficult to do in real life, because when something that contains carbon burns in enough oxygen, it mostly makes carbon dioxide. It's only when you have a very limited amount of oxygen that you can make carbon monoxide. And so it's a tough delta H to actually calculate by doing a laboratory activity. But what you can do is calculate it using Hess's law. So we're given two pieces to help us calculate this. First of all, here is the enthalpy for the combustion of carbon to make regular carbon dioxide. This is in the gaseous form, and this is in the gaseous form. And the combustion of carbon monoxide with gaseous oxygen to make carbon dioxide as well. Both of these are in kilojoules right here. I'll give you a second to copy those down, and I'm going to rearrange the table, and then I'll be able to work the problem with you. So we'll slide this over. And then we need to make some decisions. So we ultimately want to have carbon solid on the left side of the reaction. So looking at these two given reactions, we'll notice that carbon solid is on the left side right here. So let's keep it there. And let's put that reaction down as carbon solid plus oxygen gas goes to CO2 and write the enthalpy. Then let's pick another species in our goal reaction, 1/2 O2, and I'll notice I have oxygen here, but I have too much of it. I have a half of it. But you'll notice in the second reaction there's a half of it as well. And if I take this reaction and reverse it, then half of oxygen would cancel from the right side, and a half of oxygen would cancel from the left, and I'd get my okay amount. So that's my guess what I'm going to do. Another clue that might allow me to guess that I need to reverse this reaction is my goal is to get carbon monoxide on the right hand side, and I notice I have carbon monoxide on the left hand side. So let's take this reaction and reverse it to get carbon monoxide on the right hand side. So this is the reverse of the reaction, and I'll write it as CO2 gas goes to, now it's CO gas plus 1/2 O2. And then this is gaseous as well, and the delta H for this one, now that I reversed the reaction, I have to reverse the sign, and so it's positive 283. Both these are in kilojoules. Now I can take both of these reactions and I can add them together, meaning the things on this side of the arrows will come together and be right here, and the things on the right hand side of the reaction will come together and they'll be on the right hand side, and things that appear on both sides then can cancel out from one another. So omitting the signs for the phases of matter, it would be carbon plus oxygen plus CO2 on this side, and on the right side I would have CO2 plus CO plus 1/2 O2. And then when I add the two reactions together, I have to take these enthalpies and add them together as well. So when you sum two reactions, you sum the enthalpies. You'll notice that some things cancel. There's a carbon dioxide on this side and on this side. Hey, that helps because there's no carbon dioxide in my goal reaction. There's a 1/2 O2 right here, that cancels, and that means I'm going to have 1/2 O2 on this side, which is what I also want in my goal reaction. And then you'll notice what's left over is exactly what my goal reaction is here. That's why I manipulated those two reactions, was to end up with the goal reaction of C plus 1/2 O2 goes to CO, and then when I add the enthalpies together, it's negative 393 plus a positive 283, and so I end up with an enthalpy for this reaction for the production of carbon monoxide as negative 110.5 kilojoules. So that's the first example of Hess's law. I'm going to do a couple more of them, and then when you feel comfortable, then you can go on and try some homework problems like them as well. I'm going to move this paper over here. If you still have some copying down to do, you're more than welcome to pause the video as we move along. Here's my second example. Find this reaction. So here's my goal reaction. A carbon plus hydrogen goes to C2H2, all gaseous. And I'm given three different reactions here that I can manipulate to find that. So in these, you can see I've got the C2H2, I've got some oxygen going to carbon dioxide and water. I'll notice right away that I've got some C2H2 here, and that's one of my goal things, so it looks like I'm going to have to take this reaction and probably flip it around. I notice I need a carbon, and it looks like there's a carbon here in this reaction, but there's not enough of it, so I'll probably end up taking this reaction and maybe doubling it, putting a 2 in front of everything, and then when I do that I have to multiply the H by 2. And then I need a hydrogen, and I'll notice I have a hydrogen right here. I need it on this side, so I'll probably leave this reaction as is because there's one hydrogen. And after I manipulate all those, then we can add those three reactions together, and let's see if it ends up being this reaction right here. So starting with the C2H2, because that's the first time I give it, I'm going to take this reaction and I'm going to reverse it. So when I reverse the reaction, I get 2CO2 plus H2O goes to C2H2 plus 5/2 O2. Whoops, 5/2. Sorry, that's a 2. O2. And then the delta H, since I reversed the reaction, will now become the reverse, and this will be positive 1299.6. Let's see, the second reaction right here, I need 2 carbons, because I see I have 2 carbons right here, so I'm going to take this reaction and I'm going to double it. And then I have to distribute this 2 into each species inside this reaction. And so I end up with 2C plus 2O2, arrow, 2CO2, and then triangle H would be 2 times the 393.5. So I'll write that down as 2 times negative 393.5. We know that all these are in kilojoules, so I'll just put kilojoules up here so that I'm carrying my units along. Give you a second to write that one down. And then the last one is the hydrogen, and I know I need a hydrogen right here, so I'm just going to keep that one the same, H2 plus 1/2 O2, and that goes to H2O. And then the delta H is equal to negative 285.8. Alright, now if this works out, I'm going to take all of these species right here and write them on the left side. I'm sorry, yes, and then all of these species right here and write them on the right side, and we'll see what cancels. So I'm just going to write them real small right here so I can get maybe all these on one line and then all these on a line below it. 2CO2 plus H2O plus 2C plus 2O2 plus H2 plus 1/2 O2. Notice right here I have 2 O2s right here and a half O2 right here, so actually I have 5/2 O2, or 2.5. And then the things on the right hand side are going to be the C2H2 plus 5/2 O2, oh convenient, plus 2CO2 plus H2O. And I omitted the phases of matter here, but those would matter if they were different than one another. You'll notice the water and the water are liquids, and then all the carbon dioxides are gaseous here, and the oxygens are gaseous, and the C2H2 is a gas as well. And just be aware of that when you're watching your goal reactions, that you're keeping the phases the same. So things that'll cancel, the 5/2 O2 will go with this 5/2 O2. The water will go with the water. And let's see, I've got 2 CO2s right here that are going to go with 2 CO2s. And my remaining species looks like I've got 2 carbons. Hey, that's what I wanted right here. A hydrogen, that's what I wanted right here. And a C2H2 on the right hand side as well. And now, to get that enthalpy, I need to take and add all of these enthalpies together. So, try your calculator on this. Scoop this over here, let you finish writing those down. And I think this is sample exercise for those of you that are following along in the book. This is sample exercise on page 189 of the textbook, digital textbook, page 228. And I believe it's sample exercise 5.10. And the answer of adding these together ends up being 226.8 kilojoules. All right, if you're comfortable with this, you can stop the video cast right now and you can go ahead and you can start trying your own Hess's Law problems. If you want to see one more example, I'm going to do practice exercise 2 on page 228 of the digital book, and I'm going to work it right now. So if you're comfortable with it, well done. Good Hess's Law video. Thanks for joining us. If you're not, I'm going to do practice exercise on page 228, practice exercise 2. So in this one, it says, we'll pull this right over here. Calculate the enthalpy for the reaction, NO plus O gas goes to NO2, given the following information. And we're given 3 reactions right here. And we have to manipulate those reactions to end up with this. And as I've done in problems before, you see I need NO, and NO happens to be in this reaction. So let's start with that one just by writing that reaction down. And since everything in here is gaseous, I'm just going to omit the phases of matter right now just for ease of writing it down. And this has a negative 198.9 kilojoules. We know these are all in kilojoules, so I'll omit that right now. The second thing I see is I need an O, just an O atom. And there's an O atom right here, but it's on the wrong side of this reaction. And so I know I'm going to have to end up flipping this reaction around. And let's give that a try. And then I also notice that I have 2 of them right here, and I only need 1 in my goal reaction. So let's try flipping it around, and then let's also divide this reaction by 2. So when I flip this around, I end up with O goes to, and then it would be O2 over here, but that would be multiplied by 1/2 or cut in half, right? And then the enthalpy, since it's flipped around, would end up being negative 495, and I'd have to divide that by 2, because remember I divided the reaction by 2 because I only want 1 of these O's. And then the last one, I need NO2, and it looks like I've got NO2 in here, but I've got some extra things. Like if I quit right now, I'd have this O3 in here, and there's no O3 in here. And so that's what I'm going to use this middle reaction for. I'm going to use it to get rid of my O3. So I'm going to take this reaction and flip it around as well. And when I do that, I have 3/2 O2 on the now left side, and then I will have O3 on the right side. And when I reverse that reaction, remember I reverse the sign of the delta H, so it ends up being 142.3 positive value now because I flipped it around. All right, let's add these 3 reactions together, and then if it works out, we'll add the kilojoules together. And it looks like the O3s will cancel. It looks like I have here 3/2 O2. Handy, I have 3/2 O2 right here, so those go away. And then my species that are remaining that I'm underlining right here would be NO plus O goes to NO2. And it looks like I have my goal reaction. That's what I was looking for right there. And now I would take and I would add these 3 values together. And let's just do that on the calculator right here. Negative 198.9 plus my negative 495. I'm dividing that by 2 and putting in parentheses to keep my order of operations right. And then plus 142.3. And if I put that in my calculator right, I end up with an enthalpy value of negative 304.1 kilojoules. All right, so Hess's law is key, is that enthalpy is a state function. Therefore, enthalpy is the same whether the reaction is done in one step or a series of steps like this. This will lead us to methods of finding delta H, or enthalpy of reaction, from many others without using the laboratory. And in section 5.7, we'll see how we can devise these enthalpies of formation to calculate many enthalpies of other reactions.